In lab number 4, we are making 3-chloro-1-butene. This is a diene halogenation. So normally you start with a diene and then you react it either with a halogen or HCl or HBr to get the 1,2 and the 1,4 product. The 3-chloro-1-butene, if we want to go ahead and draw that, this is the 3-chloro-1-butene. When you have a diene, you always start numbering from the double bonds. It's going to be 1, 2, 3, and 4. So you can easily see that this one is the 1,2 product, because if you start with, it's obvious here that I'm starting with the 1,3-butadiene, okay? Since I have one chlorine in there, this means definitely that I'm using HCl. So if you use HCl, you're going to get two products in there. You're going to get the 1,2 product and you're going to get the 1,4 product. This is a 3 and that is 4. So we're going to get the 1,2 product where the hydrogen is going to be added to carbon number 1. The chlorine will be added to carbon number 2 by Markov-Nikov. You're still going to have the double bond between carbons 3 and 4. And this is the product that we want to make. We want to make the 1,2 product, which is the kinetic product. And kinetic product happens without heat, okay? We're going to have a byproduct in there, and that byproduct is going to be the 1,4 product, where the hydrogen adds on carbon number 1, and then the chlorine is going to add on carbon number 4. This one happens with heat, and you don't have to really apply heat because once the reaction stays like for more than an hour, it's going to be an exothermic reaction, so the 1,4 product will be created. This is going to be the thermodynamic product. But as I said, because we want the kinetic, which is the 1,2 product, we're not going to be using heat. But now we know that we have to start with the 1,3-butadiene and we're going to add HCl. Okay, so once you open your diene halogenation, open it in a new window, you guys. It's going to open up to the alkene bromidation lab. We're going to choose our reactants. So we're going to choose the butadiene. Okay, here you go. It's going to be over here. This is the butadiene. And then we're going to choose the solvent. We're going to bring our flask all the way here. Let's make this bigger. So now in the flask, what we have in the live data, we have the butadiene, we have the diethyl ether. We would need the HCl, so we're just going to go ahead and put the HCl in there. As I said, because I need the 1,2 product, I'm not going to use any heat, so you don't need to use the heating mantle in there. But definitely you would need to use the condenser, always use the condenser. And then the nitrogen gas. And then we are gonna start the reaction. Keep it on live data when you are starting the reaction. So when we start the reaction in here, this is a because I'm forming the 1,2 product. This is the kinetic product in there. Not using heat. I think it's gonna take like a couple of hours. So let's try 1 hour and see. So if we try 1 hour, see I'm forming the 1,2 product in there, but I still have some of the remaining reactants still. So I want to get rid of those. So I need to keep going on. I cannot stop. This is the second hour. So now with the second hour, see what I have? I have both products. I have the 1,2 product. This is the 1,2 product that I want. And this is the byproduct, which is the 1,4 product that I do not want. Now, because both of those are organic, I cannot get rid of those by extraction. So this is why I would need to use distillation. But before using distillation, let's get rid of the diethyl ether by extraction. So I forgot to take the TLC before and after, by the way. If you take the TLC before, if you see that the TLC is blank, it has no spot on it, just label the TLC value to be 0. Okay, the RF value to be 0 in your worksheet. That is at the beginning of the experiment in there. So we're going to go ahead and do the extraction. We're going to add some water. because again, I only have organic in there, no acid, no base. So I'm just gonna do water. And the reason why I'm adding water, because I just want to separate the two organics and I want to leave the diethyl ether. So we're just gonna take those two organics in there. There you go. Just gonna take the two organics. We're gonna dispose that. There you go. Let's return this one. Put this one back. So now in my flask, I have my two organics. I have my product that I want. This is the 1,2 product. And then I have the byproduct, which is the 1,4 product that I do not want. Again, since both are organics, I need to use the distillation. Um, the Okay, so in the distillation in there, the 1,2 product will evaporate faster than the 1,4 product. How did I know? Just go ahead and put on Google the boiling point for 3-chloro-1-butene. You're going to see that it boils around like 62 degrees. So this is the temperature that I would need to stop at. Okay. So this is going to be my distillation. Always in the distillation, we're going to put the nitrogen gas in there. And right now my temperature is room temperature, which is 25 degrees. With distillation, you move 1 minute at a time. So we're going to start the reaction. Okay, it's not a reaction actually, you are just heating your components in your flask. And once you heat your components in the flask, one of the components will evaporate faster than the other and you will collect it in the collection flask. And this is what we want. In the collection flask, we want our product, which is the 3-chloro-1-butene. Right now in the collection flask, there is nothing. In the flask, there is both. In the collection flask, there is nothing right now. So we're going to start 1 minute. So after 1 minute, we're going to bring our cursor. We did not collect anything. And see, the temperature now is 36. You're not going to collect anything unless your temperature hits 60. So we're going to do another 1 minute. Be slow in there. I don't have anything in my collection flask. A third minute. So after 3 minutes, I'm close. See, I'm 56. I'm close in there. So in the collection flask, I don't have anything. I'm just going to do 1 more minute. That's it. So after 1 more minute, this is 64. I do have in my collection flask nothing still. In my distillation, I have both. So I'm going to do a 4th minute in there, or maybe 5th, and here you go. I got my my 1,2 product. So it's going to be my 1,2 product. In the flask, I still have, let's see, in the flask, I still have some of my 3-chloro-1-butene still there. I'm gonna go 1 minute at a time until in the flask, original flask, I see no 3-chloro-1-butene. So I'm just gonna go 1 more minute in there. Just be careful, okay? So I still have the 3-chloro. I'm just gonna go another 1 minute. Okay, I still have the 3-chloro. Okay, so probably after like maybe 15 minutes or so, if you bring your cursor to your actual flask, you should see only the 1,4 product, and to the collection flask, you should see only the 1,2 product in there. Then you would know that, okay, I'm done from my distillation. I want to take my my 1,2 product. This is the product that I want to take. Okay, and the rest I'm just gonna go ahead and return back. So this is going to be my my flask in there. Okay, so in the flask I do have the let's see, in the flask here I have the 3-chloro-1-butene. This one I'm just gonna go ahead and dispose. I don't need that. I just need this one, which is the 3-chloro-1-butene. Okay, so after this, we can go ahead and do the TLC. Get the RF value for the TLC. You save to your workbook, and then we're going to do the IR and the proton animal. So we're going to do the where's that? We're going to do the IR in there. There you go. So we're going to do the IR, and again, you read your IR from left to right. So because we are looking for, let's go ahead and put them side by side. So this is what we are looking for over here. So because it is an alkyl halide, right? So there are certain vibrations that we would need to look for, and the vibrations are the C double bond C and the CCl. These are the two vibrations that we are looking at. So the C double bond C is going to appear at a higher wave number than the CCl. Use your IR table, you guys. So moving from left to right, I am looking for the alkene. Alkenes normally should show at around probably 1,100 parts per million. So I'm sorry, 1,100 centimeter to the -1. So it's this one over here. So I do have the C double bond C, and the C double bond C should appear at 1,000 centimeter to the -1. This is the C double bond C. And another one should appear around 935. So these two are for the alkenes. So the 935 centimeter to the -1, and this is the other C double bond C. And then you have your carbon chlorine, your CCl. CCl should appear, look at your IR table, it should appear in two regions. It should appear in the 700, okay, and it should appear in the 625. So those two over here are the CCl stretches. So these two are going to appear in the 700 centimeter to the -1 and the 625 centimeter to the -1. So this is for the FTIR. For the proton NMR, let's do the proton NMR. So for the proton NMR, okay, so these are peak 1, 2, 3, 4, and 5. So they need 5 peaks to be analyzed in this case. Okay, let's go ahead and look over here to see the different signals that I have. So from my structure, this is what I have. I do have a CH3 over here. So these are my 3 hydrogens. And this CH3 in there, it's going to be, it looks like it is going to be a doublet because this is a hydrogen in there. And then I do have a hydrogen here, I have a hydrogen here, and then I have a hydrogen there. Guys, hydrogen A, hydrogen B, they are different because they are in different environments. This hydrogen is cis to this group. This hydrogen is cis to the hydrogen. So these two hydrogens are in different environments. They split each other, okay? So I do have the CH3, it's going to appear as a doublet in there. This is one signal. And then I do have this signal over here. This is a CH stretch that is connected to the chlorine. This is going to be the furthest de-shielded. So if you look at position number 1, it does have a lot of peaks in there. See, it's split into a lot of peaks. This is because this hydrogen is connected to 3 hydrogens on the side. By the way, for hydrogens to split each other, they should be far away from each other by no more than 3 sigma bonds. So this is 1, 2, and 3. So yeah, this hydrogen also can split this one. So this is why this hydrogen is going to appear as 5 peaks. It's going to appear as 3 plus 1 plus 1. So it's going to be 5 peaks. So this is the CH stretch. So this CH stretch is around 5.90 parts per million. So this one's going to be the 5.90 parts per million. This is position number 1 because it's going to be the farthest downfield. It's connected to the chlorine. And then after this, it's going to be the farthest downfield. And then we have the hydrogens for the alkene. I'm expecting that CH3 to be upfield. So it's going to be in, let's zoom out. It's going to be in this position over here. It's going to be a doublet. This is position 5. It is a doublet. So this one here is going to be a doublet. And it's going to be around 1.62 parts per million. Around 1.62 parts per million. Yeah, so around 1.6, 1.59 parts per million, and it's going to be a doublet. So that one is going to be position 5. So position 1, position 5. Let's zoom out. And then the ones in the middle there, these are going to be the 2, 3, and 4. These are going to be the ones for the alkene. See how much signals these are. It says a doublet, and another multiplet in there. So this hydrogen will be split by hydrogen B into this is further closer to the chlorine. So I am expecting that this is going to be position number 2 in there. It's going to be a doublet. Actually, it's more than a doublet, but let's assume that it is going to be a doublet in this case. So this is going to be those two belong to position number 2. And it's going to be a doublet. It's made up of 1 hydrogen, and this is around 5.26 parts per million. And then we have position 3 and position 4. So we still have these 2 hydrogens. These 2 hydrogens, as we said, they are in different environment because hydrogen A is cis to this group, hydrogen B is cis to the hydrogen. So these 2 groups are different. This is why hydrogen A is different than hydrogen B. Guys, always the trans hydrogen is more de-shielded than the cis hydrogen. So I'm expecting hydrogen B to be further downfield. So this is going to be position number 3 in there, which is around 5.15 parts per million. And then hydrogen A is going to be further upfield over here. It does have 1 hydrogen, and it should be split into triplets. It's showing here as more than 3 peaks, but honestly, it should be split into a triplet because this hydrogen is so far away to split hydrogen A. So hydrogen A will be split only by this hydrogen and this hydrogen plus 1. So it needs to be a triplet. So position 4 will be for hydrogen A. And that is around, let's put the midpoint in there, around 4.43 parts per million. Okay, so again, you should see 1, 2, 3, 4, and 5 different signals, and this is actually what we see in here, 5 different signals. Do not forget that the 1 at 0, this is your reference. This is your TMS reference, so you don't take it into consideration in there. It's not part of your molecule. So you have only 5 peaks, and these are the different signals for each one of them.